So let's pick up again in the next section. This is the one where they talk about the dot product and projections and angles between vectors. So, the dot product is also called the scalar product because the result of the dot product of two vectors is a scalar. So, if you have A1, A2, A3 dot, B1, B2, B3, the way this is defined, at least by mathematicians, is A1, B1 plus A2, B2 plus A3, B3. And one thing to notice about this is that it's a number, it's a scalar. So if you if you take the dot product of two vectors, the result is a scalar, and it's easy to forget that. And you think, no, it's not. It's clear as day. But you'd be surprised when you get stressed out on an exam. You can do silly things. So number one is asking you which of these expressions are meaningful. A is not meaningful because you can't take, the result of this will be a number. Number dot a vector is meaningless. C is meaningful because this is a number times a number. Are there two C's? Oh, this is an E. Okay. So E is E is meaningless, right? Because this will be a number plus a vector doesn't make any sense. This one is meaningful because A dot B will be a scalar, and this will be a scalar product with the vector C. This D is meaningful also, and you should know that dot product distributes over plus in a nice way, just like multiplication does. So this is the same thing as A dot B plus A dot C, which is a number. F is meaningless because the magnitude of A is a number, and so you can't dot a number with anything. So I'm just ignoring 2. And these are super boring. Geez, I guess I'll do one of these. Does a person really, how many times do you really need to do this? At the same time, I don't want to be a bad teacher because I have had students that got to the first exam and didn't know how to do the dot product, and I was just shocked because you can't do anything without the dot product. So what am I doing here? I'm taking the dot product, I'm doing number 3, so this is -2 and -5 is 10, and 1/3 and 12 is 4, so the dot product here is 14. And yeah, so they're all, I think these are all just totally easy. Maybe we should do one here with component notation too, like number 7 maybe. So number 7 would be 1 and 5 is 5, and -2 and 0 is 0, and 3 and 9 is 27, and so this is 32. And let's do number 9, because that looks like it actually takes some thought. So number 9, they're saying find A dot B. And in general, this formula is proved in the section, and you have to know this. This is the way physicists define dot product. And so that's what you can use to do number 9, use this formula, because now they give us the magnitudes and the angle. So the answer here is going to be 6 times 5 times cosine of 2 pi over 3, and I'm just going to call that done, so, or am I? So that's 1 pi over 3, and then 2 pi over 3 is going to be 2 of those, I guess. What is it? 3 pi over 3 minus 2 pi over 3 is pi over 3, and yeah, so that means that this is going to be sort of like that, and so this is going to be minus 1/2. So this is negative 15. Negative 15. And so number 10 is similar. Sorry I'm such a butterfingers. And we're totally lost now. Hold on, I'll get back on. So 11 and 12 are sort of, you know, thought-provoking questions, I guess. And God, I'm so terrified now of sending us off to some crazy place. Let's look at number 11. So what happens if you take the dot product of a unit vector and some other vector? You know, because of this formula, cosine theta, what is a unit vector? It's a vector of length 1. So this simplifies to just the magnitude of v times the cosine of the angle. And what they're giving you here is, I guess this is an equilateral triangle, all sides the same, so that means 60, 60, 60. And that means that if the magnitude of v is, if the magnitude of u is 1, and it really is a equilateral triangle, then the magnitude of v is 1 also. And so in that case, u dot v is just cosine of 60 degrees, which is 1/2. So the answer to number 11 is 1/2. So that's kind of interesting. And what else have we got? Find the angle between the vectors. Yes, that is an important thing to be able to do. So 15 and 20, we're kind of going backwards now. And let's try to find the angle between, number 15, try to find the angle between A and B. And, you know, you've got this formula, A dot B is equal to the magnitude of A times the magnitude of B times cosine of the angle. And you can solve for the angle here, and you get inverse cosine of A dot B, which remember is a number, divided by this number, the product of the magnitudes, is equal to theta, and that's what's going on in 15 and these other problems. So what is the answer for number 15? The dot product of, we're going to need to figure out the inverse cosine of, let's do the dot product on top, so that'll be, oh my god, it's going to be just god-awful. Minus 8 times the square root of 7 plus 18. And what is the magnitude of this? It's the square root of 64 and 36, which is 10. And what is the magnitude of this? It's the square root of 7 plus 9, which is 4. That's a little bit merciful. And whatever that is, I'm not sure what that comes out to be. But it's theta, and you'd have to do this on a calculator. And so let's keep going. So what about this? Well, you have to pick one of these to be the sort of play the role of the origin for number 21, let's say. You know, you really want to think of it as A, and then here is B, and here is C, where this is the angle, sorry, mistake. Not the angle, the vector AC, and this is the vector AB. And you have to use you know, this formula with these two vectors, which you get by basically subtracting the point A from both of these. And this is just a three-dimensional version of the same thing. Right. Determine whether the given vectors are orthogonal, parallel, or neither. So what does orthogonal mean? So A dot B equals 0. This is the, so if A and B were orthogonal, then the dot product is 0, and if the dot product is 0, they are orthogonal. That's the definition of orthogonal, and geometrically it just means perpendicular. So for A and B here, let's do number 23A. And so what's the dot product of these things? It's minus 30, minus 24, plus 14. And the answer is that they are not orthogonal. Now, how can you tell if they are parallel? So if they're parallel, they go in the same direction. So could it be true that you know, they have this kind of relationship where maybe this is A and this is B and they just differ by a scalar product? I don't think so, because there's no scalar that you can multiply into A that gives you B. If you don't like to think hard, they're going to be if they're parallel, then A cross B, when you have three-dimensional vectors, are going to be 0. That's because, remember, this gives you the area of the parallelogram. And so the only way the area of the parallelogram is going to be 0 is if the parallelogram is degenerate or collapsed on itself. So an easy way to check if, or I don't know if it's easy or not, it's actually kind of hard to compute the cross product, but one way to check to see whether or not two vectors go in exactly the same direction is to take their cross product. So what else? Determine whether, yeah, so maybe these are, so should we do maybe 23b, we should try to do one where the answer turns out to be yes. Number 23b, oh, it's not vector b, it's just b. So you get minus 12 plus 12, and it is equal to 0, and so the answer for 23b is yes, they are orthogonal. This is kind of boring the hell out of you probably, isn't it? Maybe I want to remind you of a basic fact here. So if you've got an obtuse angle between A and B, and you can reverse the roles here if you want, then A dot B is going to be less than 0. And you already know that perpendicular right angle means the same thing as A dot B equals 0. And you can also test for acuteness of the angle. So if they're acute like this, then A dot B is positive. So it's true that the dot product gives perpendicularity, but it gives more information. If it's positive, then the angle is acute. If it's negative, then the angles are obtuse. And that all follows from, where's that formula? This formula. And the reason is that cosine is negative for obtuse angles and positive for acute angles and 0 for 90 degrees. And so the sign of this doesn't depend on these magnitudes because these are always positive quantities. It only depends on the sign of cosine. And so that rule that I just explained is just follows from the properties of cosine. What else have we got? Use vectors to decide whether the triangle given by these points is right-angled. How do you do that? So just to sketch the solution to number 25 here, what you would do is figure out the vector PQ, figure out the vector PR, take their dot product. If it is 0, then it's a right-angled triangle. And one thing that worries me a little bit about that is you have to check it a couple ways, don't you? So one problem for me, like doing, I guess one of many problems of me doing this in sort of a chatty style, not having done any of the problems myself before, is that, you know, if this turns out to be PQ and this turns out to be PR, then great, the dot product will be 0. But what if you have a right triangle like this, and you accidentally take this to be PQ, and r, then this will be PQ, and this will be PR. And you'll take the dot product of PQ and PR, but it will not be 0. Then you could wrongly conclude that the triangle is not right, whereas the way I drew the picture, I do intend for it to be right. So you really need to try 3 possibilities. So this is the case where P is playing the role of the origin, but you also need to check where Q is playing the role of the origin and where R is playing the role of the origin, which is kind of exhausting. So I'm not gonna do it. I think there are faster ways than checking all 3 corners. What could you do? You could take the cross product here, and then you could compare that to I don't know. Yeah, so I'm just trying to think, if this is a right triangle, then it makes half a rectangle, and the area of the rectangle has something to do with the cross product. So I don't know. You're probably smarter than me. You see if you can think of a faster way to do that with the cross product. Find 2 unit vectors that make an angle of 60 degrees with this. That's a good exercise? So let's do that. So let's try to draw a picture here, and I'll give you some straight lines. And let's look at 3, 4. So 1, 2, 3, 1, 2, 3, 4, and here is V. All right, and they want us to find 2 unit vectors that make a 60-degree angle with that thing. So let's put the unit circle here. It's going to be really small, actually. Got to turn the ruler off. So if that's the unit circle, what they're asking for is this little unit vector. Looks like it's going to be something like maybe even just the x-axis, you know. The way it drew, I don't know, it can't be like that, can it? But you're just looking for 2 unit vectors. That's 2 vectors that occur on the unit circle, so that's 60 degrees and also that's 60 degrees. So how can you do that? I guess you could do it with trigonometry. What is the angle that that V is making with the... What's the angle that V is making with... Oh, Christ. Excuse me. What's this angle that V is making with the horizontal axis? That's just going to be the angle that that V forms with I, and so what is that going to be? That's going to be inverse cosine of V dot I divided by the magnitude of V. And is that going to be something nice? This is just going to be the first coordinate, so this is cosine, inverse cosine of the first coordinate of V, which is 3, and the magnitude of V is the square root of 9 and 16, which is 5. So it's inverse cosine of 3/5. And we could figure out that angle in speed crunch. Now I'm getting insecure about taking up your whole day, but I'm a recording. If you find this boring, skip ahead to some other part or just do these problems yourself, which is maybe even better. So what I want is a cos of 3/5. And I think I have this set on radians. Let's put it on degrees. It'll be a little bit more comprehensible. So this is 53 degrees. I'm just going to call it 53.13 degrees. 53.13 degrees. And, all right. Oh, good Lord. So here we've got this 53.13, and I'm trying to find two unit vectors that make a 60-degree angle with this thing. So how can I get 60 degrees? I need sort of, this is going to be what do I want? I want 60 degrees minus 53.13 degrees is going to be something like, you know, minus 6.87 degrees. So this is negative 6.87 degrees. And so how do I get this point on the unit circle? It's just going to be cosine of minus 6.87 comma sine of minus 6.87. And that's 1. Okay, so I'm just using the fact that unit vectors lie on the unit circle and the connection that I know to trigonometry. If you find that confusing, feel free to do it some other way. And to find the other one, you could just do, 60 plus 53 is going to be 113. Now deal with 113.13 degrees and do the same trick with sine and cosine. And that gives you the other one. Okay, so that was an interesting exercise, I think. What else have they got here? They've got, oh God. Hold on one sec. So 35 through 40 are important problems because they're about scalar and vector projections. So you need to understand those. So how do those work, So usually the setup in the book is you're looking at the projection of this vector, let's call it B, onto some vector A. And what you do is you sort of drop a perpendicular here. And now this length is the scalar, the magnitude of this length is a number, and that's the scalar projection. And the notation for that is comp onto A of B. And if you want to know what this is as a vector instead of as a scalar, you just multiply. So the notation for that is the scalar projection. That's the projection onto A of B. And it's just the scalar projection, which is a number, times the unit vector in the A direction, which is this. And it turns out that the formula, if you just use, actually it's really simple to derive the formula. And to be honest with you, I frequently forget it and have to rederive it. It's just the cosine. So this side of the triangle is just the cosine times the magnitude of B, because that's the hypotenuse here. So comp onto A of B is equal to B times the cosine of the angle. And the cosine of the angle is the same thing as A dot B over A B, and then this cancels with that, and you get A dot B over the magnitude of A. Okay, so fantastic. And so now if you substitute that in here, this becomes A times A dot B over the magnitude of A squared. So this is the vector projection, and this is the scalar projection, which is just a number. And these problems 35 through 40 are just asking you to compute that. So for, let's see, let's do 37, because it feels slightly more general to work in 3 dimensions. So let's just use the formula. So the scalar projection onto the A component of the vector B is that formula that we just derived, A dot B over A, and so that is 3 times 1 is 3, plus 12 minus 6 over the magnitude of A, which is the square root of 9 plus 36 plus 4 is 7. And so this is 9 over 7. That was considerately simple number. Guess that's why James Stewart makes the big bucks. And so this is the scalar projection, and to get the vector projection, you just do 9 over 7 times the normalization of A. And so what is A over the magnitude of A? We already know that the magnitude of A is 7, and so this is 9 over 49 just times A. This is a 9, and this is going to be the vector projection. Oh, I did it backwards. Onto A of B. And, what is this explicitly? So it's 9 over 49 times the vector 3, 6, negative 2. And you could multiply this in by scalar multiplication if you feel like it. What else? So I need to learn not to touch this thing. This is a good question, number 52. I'm not going to do it, but you should be able to do that. And number 51 also is pretty simple. This one, number 57, if you look at this section, it's using the fact that work is equal to force dot distance. And that's an important thing to be able to understand if you're going to be a scientist and possibly be doing something physics heavy in life, but I didn't emphasize that in class, so I won't make a big deal out of it now. Number 43 looks like could be interesting. So it says if A is this vector, find a vector B such that it projects onto A and has a shadow of length 2. It's basically asking for a vector B that makes a shadow of length 2 when you project it onto A. So let's take a look at number 43. So the picture is you have something A here, and that has the, we're going to say that it's 3, 0, minus 1, fine. And what we're looking for is some unknown vector B. And one thing we know about B, though, is we want the length of the shadow of B projected onto A to be 2. So that's kind of a cute problem. So let's call B, right now we don't know it. It's just, let's call it B1, B2, B3, and can you see that there are going to be sort of infinitely many choices for B? It's not going to be uniquely determined. So we could pick the B of, oh, you know what would be a really stupid way to do this is we could just scale A so that it has length 2. That's fair. Now the projection is just totally trivial, isn't it? Do you hate that solution? I kind of like that solution. Let's do that. So one solution is we'll just do C times the norm of A. So we're trying to find some C so that C times A normalized has magnitude equal to 2. We're going to solve this for C. And so what is the magnitude of A? The magnitude of A is the square root of 10. And so we want C times what is this? So C times, this is just gonna, I'm kind of confusing myself, because this is going to be equal to, oh man, this is going to be equal to 1. So what we really need to know is actually C is definitely equal to 2. And now we just need to take the normalization of A, which is 1 over the square root of 10 times 3, 0, negative 1 over the square root of 10. This is just the normalization of A. And the final answer is just going to be 2 times that. So the solution is you could take B to be 6 over the square root of 10, 0, negative 2 over square root of 10. And that would be this trivial solution where you just have a solution that's the scalar multiple of A, and its projection is sort of just itself, its vector projection is itself. If you want to take one of these other solutions, you know, I'll leave that to you. So there are infinitely many other solutions, so find one of these if you want. That would be a good exercise. What else have we got? Okay. All right, I don't like any of these. I'm declaring us done with this section. So let's pick it up again in the section on cross product, and there's a lot to this section. You know, cross product takes two vectors and two three-dimensional vectors. It's only defined in three-dimensional vectors, and gives another vector that is orthogonal to the given two vectors. And you know that the so can I maybe try to draw a picture of that? If this is A and this is B, then if you take their cross product, you're going to get something that is at right angles to both. And so here's A cross B. Oh, and so we should pay attention to the right-hand rule. The right-hand rule says if you take your right hand, so see how I did this? This is actually minus A cross B, and the reason is something called the right-hand rule. So if you put your right hand in the position of going from the first one down to the second one, then the direction is the direction that your thumb points, which in this case is down. But by making the cross product negative, I made my picture right, at the expense of being a terrible expositor. Now, important thing about the cross product is that its magnitude is the area of the parallelogram, and also if you just do some geometry, this turns out to be the magnitude of A times the magnitude of B times sine of the angle between the two, which is how, is that how physicists, yeah, physicists probably define the cross product as the vector with this magnitude that has direction determined by the right-hand rule. And so that would be another way to define everything. And so that's all you need to know, except how to compute this stupid thing. So I find that students get really good really fast at actually computing the dot product. But let's do it once just for the hell of it. Let's do number 1. So I find it to be efficient to sort of stack them elementary school style like this. We'll do A cross B. And so what is this going to be equal to? So it's going to be I times 0 minus 8 minus 16, which is 16, and now it's minus j times 0, 0, so actually this is 0, plus k times 48. And so that's the, there you have it, there you go, that's the answer. And here it says verify that it's orthogonal to both A and B. So let's do that. Let's this this and other notation is just 16, 0, 48. So is it true that this thing is really orthogonal to both of these? So 16, 0, 48 dot 6, 0, minus 2 is going to be, you could divide this one by 16 and your life would be much easier, because then it would just be 1, 0, 3, and it would go in the same direction, and then, that's not going to change orthogonality. So it's actually much easier to do 1, 0, 3 dot 6, 0, minus 2, and then you get 6 minus 6, and that is equal to 0. And so, if you're still feeling skeptical, try that. Actually, it's really easy to see that if you dot these two, then you get 0, because all the zeros sort of line up, and it obviously is 0. Here's a little bit. This is a little bit more abstract. I think I really suggest you do number 7. That's kind of interesting. So this would be, how could you interpret this? You could interpret number 7 as saying something about two different space curves, but I don't really feel like I could articulate it very well. But think about what it might mean. So here it says, find the vector not with determinants, but by using the properties of cross products. And so what they're saying here is, oh my god, I touched it again. I thought I'd learned my lesson. Hold on one sec. So with these unit vectors, the plus or minus unit vectors are sort of closed under cross product, and you can figure out what these things are just by thinking and drawing pictures. You don't need to do any calculation. So here's I cross j. What is that going to be? So here is your I, and here is your j. And if you do I cross j, then using the right-hand rule, you can see that it's going to go up like this, and its magnitude is going to be this area, but that's a 1 by 1 square, so it goes up magnitude 1, and so it's just k. So this becomes k cross k, and that is 0, because if you look at the if you look at the area of the parallelogram that's spanned by k and k, it's a totally degenerate parallelogram, because these two vectors are the same. So you see how it just kind of collapses down on itself when they're the same. And so the answer to 9 is 0. It would be the 0 vector, though. So it's a vector with magnitude 0, and so it's just the 0 vector. And number 10 here, you can distribute. So the cross product distributes over sums and differences in a nice way, so multiply those in. And it also behaves sort of like FOIL for binomials, and so you can FOIL these out, which is a good exercise. Number 13. All right, so the cross product is the vector product, and so number 13, hopefully these will all be really easy to decide whether these are meaningful or not. So A is, C is, E is not, because this is a number cross product. A number makes no sense. And similarly, B makes no sense, D makes no sense, and F does make sense because it's a vector dot a vector, which is fine. Okay, so don't touch that scroll bar. What have we got here? It's just asking you about the right-hand rule. So find the magnitude of the cross product. That's asking you to do, if you can kind of complete the parallelogram here, then just use the formula height times width, and to find the height you have to do a little bit of trigonometry using 5, and so the height here is going to be h equals 5 times sine of 60 degrees, And then for the base, you can just use 10. So 5 times sine of 60 degrees is square root of 3 over 2. So it's going to be kind of ugly. But that would be the magnitude, and the direction just follows from the right-hand rule. So if you make your fingers go, the fingers of your right hand go from U down to V, then your thumb is going to be stabbing into the page. So the answer for 14 is into the page. What about number 16? It says, the figure shows a vector A in the xy plane and a vector B in the direction of k. And it gives you their lengths, and you're supposed to find the magnitude of the cross product. So it's just going to be, because they're orthogonal to each other, the parallelogram that they make is just going to be a rectangle, and the area of the rectangle is just going to be base times height, which is 6. And so the answer to A is 6. B says use the right-hand rule to decide whether the components of A cross B are positive, negative, or 0. So here you've got to make your right hand curl up from A to B. That makes your thumb go this way, and that means that the x-coordinate is positive, the y-coordinate is negative, and the z-coordinate is 0. This is just a dumb computation exercise. Find 2 unit vectors orthogonal to both of these. So what do? You take their cross product, right? And then you normalize it, and it'll be plus or minus that. What else have they got here? Proving the properties. I'm not going to ask you to do that on the exam. I think it's too hard, but if there were if there are a lot of math majors in the class, I would make you do this. But number 29, find a non-zero vector orthogonal to the plane through the points P, Q, and R. How do you do that? So these are 3 points. 3 points determine a plane. If you look at the vector PQ and the vector PR, something orthogonal to the plane is just going to be the cross product of PQ and PR. So the answer for 29 here is going to be the cross product of PQ and PR. And now use the parallelogram property as it relates to the magnitude of the cross product and divide the answer by 2. That's how you get the area of the triangle. It just makes half a parallelogram. You should draw a picture. What else? Oh, the parallelepiped. So this is interesting. Let's do number 33. So this has to do with the scalar triple product. So I don't know exactly what these things look like in 3-dimensional space, but let me try to draw something plausible. So let's say that's one, that's another one, and this is another one. It's supposed to be correct in my handwriting. It's not doing a very good job. So these things make together a parallelepiped, which looks sort of like this. That's not very good. Okay. So a parallelepiped is it's the 3-dimensional analog of a parallelogram. So all faces of this 3-dimensional rectangular-like thing are parallel to each other. And if this is A, B, and C, then we've seen that, if you've read the chapter, you know that the area of this thing is A dot B cross C, and you could do it some other way if you want to. That won't change anything. And what this amounts to is the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. And so to do number 33, for example, you just do the determinant of 6, 3, minus 1, 0, 1, 2, 4, minus 2, 5, and what does this turn out to be? This turns out to be 6 times 1 times 5 is 5, minus 4 is 9, minus 3 times 0, minus 8, so this could just be plus, and now we've got minus 1 and 0 and minus 4, so this could just be positive 4. Now you add all these things together, and this is 54 plus 24 plus 4, and I don't know what that adds up to. Whatever that is, that would be the volume of the parallelepiped. There goes my fat hand causing problems. Okay, and so number 35 and 36 are really similar, but instead of using, you know, A, B, and C, you have to use PQ, PR, and PS. So those are going to be your 3 vectors, and otherwise it's going to be just the same as these. Verify that the vectors are coplanar. How can you do that? So you've got 3 vectors here, and they're supposed to be coplanar. So if they all lie in the same plane, then the parallelepiped that they make will be totally flat. It will have no height. And so what you need to check is that the volume of the parallelepiped is 0. So what you're checking here is that if you do the scalar triple product U times V cross W or some other permutation, it turns out to be 0. So that's what you need to check to do 37, and you should draw the parallelepiped with 0 height and kind of try to understand what I'm saying about that. Use the scalar triple product to determine whether the points lie in the same plane. Again, this is just the problem 37, but you use AB, AC, AD as your vectors. This is a torque question. I've done it several times. Let's see if there's a different torque question. How about number 41? So, you know, I think some people don't understand what torque is. Torque is basically twisting force. And, you know, I'm sure there's an article on Wikipedia that would probably help you understand it. The problem is that sometimes eggheads get a hold of those articles on Wikipedia and try to make them so precise that they are no longer comprehensible, which may very well be the case with the torque entry, but maybe you should go ahead and have a look at it anyway if you really care. So it says, which one are we doing? Number 41. So there's a wrench that is 30 centimeters long, lies along the positive y-axis. So here's a wrench, and it's 30 centimeters long. Let's just remember that. Maybe I'll write it into the diagram in a second. Lies along the positive y-axis, so that's about right. Pardon my fat hand. And I'm going to commit suicide. And what else? So it grips a bolt at the origin. A force is applied in the direction. So they're talking about three-dimensional coordinate system, so it might help with our visualization if I added that to the picture. There's Z, there's X, and here's Y with the wrench going along Y, and they're saying a force is applied in the direction 0, 3, 4. So I guess those are supposed to be in centimeters. So 3 compared with 30 is actually not very much. It's going to be like right there. So this is going to be 30 on the y-axis. This is going to be 3 on the y-axis, and the z-axis we're going down to minus 4. Okay. So, you know, minus 4 is not going to be much either. So it's something like that, and this is in the yz plane, this little thing here. So this is the force vector that they are talking about, and if you want to imagine the vector, or the wrench really being turned, you know, you can imagine it being put at the end of the wrench, and so there's somebody's hand sort of, I guess it's kind of hard to imagine somebody's hand. I guess somebody's hand is applying force like that. Can you imagine that? In that direction with that magnitude. So what you need here is this angle between the two, and then you just, the torque, tau, is equal to the vector v, which in this case is just 30 times j, and cross the force, which in this case is 0, 3, minus 4, and so what they're asking for is probably the magnitude of the torque, right? Find the magnitude of the force needed to supply that much torque. Okay, so okay, so this is just the direction, and so there should be a c in here. So what they're saying is this is the direction of the force, but we haven't decided on the magnitude yet. So to represent the magnitude in this formula, I'll just use some scalar c, and so I'll multiply it in here. Let me just adjust this a little bit. So this will be 3c, and this will be minus 4c. So c is something that we're going to need to solve for. And the magnitude of the torque is obviously the magnitude of the cross product of v and f, and that is going to be the magnitude of v times the magnitude of f times sine of the angle between them. Okay, so what is the angle? Let's just, the angle isn't going to change based on what c is, so let's just find the angle between, 0, 3, minus 4, and j. So what is that? That's going to be that thing, dot j, divided by the magnitude of this, which is the square root of 25, which is 5. And we have to apply inverse cosine. And so this turns out to be inverse cosine of 3/5. And what is that? We already done that before. Wow, weird. It's that same angle, 53.13 degrees. All right, so that's the angle theta, and so now we know what the so let's work that in here. Now we need to take sine of this angle, because that appears in the formula for the magnitude of torque. So let me just get sine into the mix here. I'm not sure what just happened. Stupid thing. So I want to take sine of inverse cosine of 3/5, and that is 0.8. That's a nice number. That must be why they use that number. So now we know that sine theta is 0.8. And what have we got? So let's look back at this formula that we're using. We know that the wrench is 30 centimeters long, so obviously that's the magnitude. So we've got 30, and what's the magnitude of the force? The magnitude of, here's what we're using for the force. So the magnitude of that thing is going to be c, let's just assume c is positive, times the square root of 9 and 16 is 25, so it's going to be 5c. Right, so that's the magnitude of the force. So the magnitude of the wrench times the magnitude of the force, which is 5c, times 0.8 is equal to the magnitude of the torque. And now they're telling us that they want the magnitude of the torque to be equal to 100 Newton meters. And there's got to be some unit conversions in here because this is in centimeters, and I guess this is in centimeters too, and this is unitless, so we've got 0.3 meters times 0.05 meters times c times the dimensionless quantity 0.8 is equal to 100, and now you just solve for c and that's it. That's an interesting problem. So what else have they got? Number 43 looks kind of deep. It's probably, just judging by how complex it is, it's probably too hard for an exam question, but it looks fun. We just spent a long time doing a problem though, so let's see if we can find something simpler. This is actually totally dumb. It's kind of interesting. This is sort of like the difference of, this should be sort of like the difference of squares. Try that using the fact that this should work like binomial multiplication. These are all proof questions. What about number 49? So if a is non-zero, if this is true, so what does this mean? This means that the angle between, no, okay, so this is false. What happens if you use the formula magnitude of A, magnitude of B, cosine theta? This would be magnitude of A, magnitude of C, cosine theta 2, and it's one equation and two unknowns, and so there's going to be a lot of variability in the solution. So the answer to A is no. And what about this? Here the answer is yes. And is that right? I think the answer is yes. You tell me why. Yeah, you tell me why. My intuition tells me that the answer to B here is yes, but I'm not going to go through it. So let's say that this is done.